Okay. Do you know what's going on? A little bit, okay. So basically, this chapter is about testing, okay? Last week, we finished t-test, right? T-test, t-statistics, which is only for one coefficient, okay? And then we talk about one-sided, right? Left side and right side. You must know how to calculate t-statistics, okay? You need to know the formula. So basically, I'll show you the estimation result like this. Okay, this is the estimation result. And you need to be able to calculate the t-statistics, okay? The coefficient divided by the standard error of itself. And then you compare with our critical value. Is it in 1%, 5%, or 10%? I'll continue with my teaching. So I'll continue with, okay, two-sided. And this is the most common case in practice, two-side tests, okay? Here, we test our null hypothesis H0, which means beta j equals 0, against our alternative, which is H1 hypothesis. Beta j doesn't equal 0. This is more general because here we don't know which direction, okay? There's no direction assumed. We just want to know, does X, J matter at all, positively or negatively, okay? So since we don't know the direction in advance, we reject H0 where beta J hat is too large in either direction. Okay, is it too positive or too negative? That's why now we have two rejection regimes, okay? One in each tail, right? The right tail and left tail. So here, let's see. We take the 5% significance level in half, right? Because right now this is two sides, okay? So 5% in half, that means 2.5% in the left tail, another 2.5% in the right tail, right? But here it's 0.025, just means 2.5%, okay? So in this example, our critical value is positive or negative 2.06, okay? Those are critical value. And what is the decision rule? And this is important part to remember, okay? We reject H0 if the absolute value of the t-statistic is greater than 2.06. Okay, so here we use the absolute value here. And this is our decision rule. Basically, it doesn't matter if t is positive 2.5 or negative 2.5, all right? Okay, so here I showed you the rejection rule. And here you need to know that the two sides tests are the default. This is the default test in econometrics. And this is what you'll use in most papers and in most cases in this course, okay? We're gonna use two-sided. Because basically, do you know that suppose xj, can we say that xj is positive for y for sure? Can you? Just like the price. If price goes up, can we say that it it will definitely has a negative effect on the consumption. Depends, right? Because we have so many different categories. So in this case, we are not sure about the sign is positive or negative. That's why we use the two-sided, okay? So this is the default in econometrics. Let's practice two-sided testing with a new example, okay? So here, what determines college GPA? Here is the regression results, all right? You will see this one. This is the regression results. Okay, so this is the fitted model. We have HS GPA and ACT score, okay? This skipped means lectures missed per week. This is observation and R squared. Let's test one by one. The first one, what is the T statistic of HS GPA? 4.38. How we get this? Can you tell me how we get 4.38? You need to use the coefficient divided by its standard error, right? So here it's 0.412 divided by 0.094. Can you calculate with your calculator? Is it 4.38? So this is for HS GPA. Next one is ACT score. Okay, so I highlight in pink. You have to know how to get those two statistics, okay? You have to know. Is it 4.38? Okay, great. So this T statistic for HS GPA, which is 4.38, greater than our critical value, even at the 1%. So right now you need to know C 0.01, which means critical value at 1% significance level, okay? So this is our critical value. This one is greater than, right? That's why we can reject H0, which means this HS GPA has a effect on our college GPA, all right? Same here, but for ACT, our T ratio, here we got 1.36, right? This one is less than the critical value at 10%, okay? Be careful about here. This is 10%. So basically, the effect of ACT is not significantly different from 0 because we cannot reject H0 here. Not even at the 10% significance level. Actually, 10% is very loose. This critical value is very loose. It's not strict. And here, we're going to use the two-sided testing to test our skipped. Okay, so you see here, we use T skipped absolute value. Okay, so which is negative 3.19 absolute, and it's greater than our critical value at 1%, 2.58. Which means we can reject our H0, right? Skipping lectures significantly affects GPA. Okay, let me repeat. Skipping lectures significantly affects your GPA at 1%. Okay, be careful about this. So here is two-sided, right? This is what we just learned, two-sided. So we use the absolute value. Clear about this example? So for T ratio, we're gonna test each by each, okay? Each by each. ACT, what is ACT? It's from your high school. The score is from your high school, is it? Okay, this variable, people often assume matters for college performance, but in our example here, it turns out it's not significant here, right? So this is a nice real example of why we test instead of just assuming. Assuming is your hypothesis, and you need to test it, okay? This slide gives us a name for what we've been doing, plus some numbers worth to memorize, okay? So let's see the definition. If a regression coefficient is different from 0 in a two-sided test, the corresponding value is said to be statistically significant. All right, so this is the definition. Significant just means the t-test rejects H0, right? Rejects our null hypothesis. Now, let's see the practical rule of thumb. Remember, if the degree of freedom is large enough, okay, for the normal approximation, DF means degrees of freedom. So we can use this rule of thumb to determine, okay, to reject our null hypothesis. If the T ratio, the absolute value, okay, here, greater than 1.645, so this is the critical value at 10%, and 1.92 is the critical value at 5%, same as 2.567, this is the critical value at 1%. So basically, you see that from 10% to 1%, the critical value is larger, okay? That means it's more strict. Okay, so when you do your paper, actually, you need to use those critical value to determine your variable, is it statistically significant or not, all right? You'll see those values constantly, okay, in this course and in every empirical paper you read. Basically, if you read an empirical paper, they don't tell you they use those critical value, but you should know they use this one. And to see that, if it's 10%, so basically we use the L star is this one, the star, to represent. So 1 is for 10%. So how about 5%? Can you guess? Okay, 1. How we call this symbol? Star. Okay, 1 star for 10%, 2 stars for 5%. So how about 1%? 3. Yeah, exactly. So right now, if you read the paper that you want to follow, you're gonna see the estimation result. Let's see, negative 0.1. This is the estimation result. This is the beta hat. And below that, they're gonna show you something in parentheses, okay? Suppose the 0.0 0.02. This is the stand error of that estimate, okay? Basically, this is beta hat. This is stand error of beta hat. And can you calculate the t ratio here? Use your calculator to calculate. Negative 0.1 divided by 0.002. Let me see. Oh, minus 50. This is just for my example, okay? Basically, this is very different from 0, okay? So you're gonna see that they put a 3-star here. What does it mean? That means this estimate, okay, the coefficient of that x is statistically significant even at 1% level, all right? So right now, I hope you can read the economic paper. The rule is that if your t ratio is greater than 2, that means you are almost always significant at 5%, all right? As long as your t ratio, the absolute value is greater than 2. That's the handle quick check when scanning a regression table, because you're going to get the regression and you need to decide your significance level. Next one. So what we learned so far, we always test it against 0. Have you noticed that, right? Is it greater than 0, less than 0, or equal than 0? But sometimes we want to test against some other specific value, okay? Let's see, is the effect equal to 1 or equal to -1, okay? So this is the general null hypothesis. That means before our hypothesis is something like H0 beta j equals 0, right? But here, let's generalize it. Right now, our null hypothesis is beta j equal aj or not. Where aj is whatever value we want to test, okay? It's not necessarily 0, right? This is the hypothesized value of the coefficient. And next one, we have the general t ratio, okay? This is the general t ratio. T equal estimated minus hypothesized value, right? And then divided by the stand error of itself. Here we have beta j hat is the estimation coefficient minus aj. Aj is our hypothesized value, right, from our hypothesis. And then divided by the SE of beta j hat. Everything else stays the same, right? Same critical value, 1%, 5%, 10%. We're gonna use those one as usual, okay? So this is something you cannot change, okay? It's from the table, okay, statistical table. So here, what changed is your hypothesis, okay? Same rejection rule, same logic. No matter you use one-sided or two-sided, okay? Depending on H1, the only change is with subtracting AJ instead of subtracting 0, right? So this is the good way to frame it. This is the same tool, just more flexible, okay? This is our general null hypothesis. This is more flexible. Now we can test any specific claim about beta j, not only no effect. No effect, which means it equals 0, right? Okay, I'll give you 3 minutes. Could you read this example and then we'll discuss it together? So you should notice that this is the estimation result. Okay, this is your hypothesis and this is your T ratio. And then we compare it with our 5% critical value. I'll give you 3 minutes. Here. If you want to follow, at least you should have my slides, all right? Okay, so let's see here. This is the example of testing against a value other than 0, okay? So this is our model. Log crime hat equal negative 6.63 plus 1.27 log enroll. So here you see our y and x, they are in logs, both of them. So how we interpret our estimation here, 1.27? Is it units or semi-elastic or elastic? Remember, if both x and y, they are in log form, yes, elasticity, okay? So 1.27 is our percentage interpretation, right? Elasticity. You should be able to interpret, okay? Which means a 1% increase in enrollment is associated with about a 1.27% increase in crime, right? Because we got positive here. So they have the same direction, positive relationship. Okay, so there is our interesting question. Is this effect exactly proportional? What does it mean? What is the meaning proportional? It means that does crime increase by exactly 1% when enrollment increased by 1%? That's why our null hypothesis here is H0 beta log enroll equal 1, not 0 anymore, right? Because we want to know, does their effect is proportional or not? Okay, so that's why we have our hypothesis here, H0 and alternative H1, which means beta log enroll doesn't equal 1. And this is the two sides, okay, two sides. How you calculate the t statistic here is something different, okay? Right now, you need to use the estimated coefficient 1.27 minus our hypothesis, right? So you need to know where does this one come from. In the exam, you have to show me how you calculate your T ratio, okay? And this one is approximately 2.45, which is greater than 1.96 at 5% significance level, all right? So that means we can reject our H0 at 5% level. Okay, clear about this example? You may say it again somewhere. The conclusion is that the elasticity is statistically different from 1, okay? Crime increases more than proportionally with enrollment. Which means bigger schools don't just get more crime because they have more people. Crime rises faster than that, okay? Next one, new concept about p-value. Have you heard about it? P-value? Okay, great. Okay, I'll give you some time to read the slides, okay? And then I'm gonna summarize for you. After you finish reading, can you tell me what is the keyword here? I know a lot of information here. What is the keyword? Okay, you should be familiar with 10%, 5%, and 1% right now. Let's see what does it mean here. If the significance level is made smaller and smaller, let's say even 0.1%, very strict, there will be a point where the null hypothesis cannot be rejected anymore. And this is the thing that we don't want to. Basically, we always want to reject our H0, right, in favor of H1. So if we keep lowering the significance level, at some point, the critical value goes so strict that you can no longer reject H0. Makes sense, right? Because a smaller significance level means you are demanding stronger evidence before rejecting. Okay, too demanding. Because you want to avoid the mistake of rejecting a true H0. So here is the definition. The p-value is the smallest significance level at which you can still reject H0. Okay, let me. What does it mean? So before I showed you this one, right? Let me just use this. So the T statistic is extremely large. It's about -50 something. So basically, this one is significant at 10% for sure, and also significant at 5% and 1%. But that means you need to choose the smallest significance level, which is 1%, okay? So this 1% gonna be our p-value, which is 0.01 or even less than 0.01, right? Sometimes less than, because this one is our critical value. It should be less than it in order to be significant, okay? A small p-value is evidence against the null hypothesis because one would reject the H0 even at small significance level, okay? So basically, you need to check your p-value as long as it's small enough, it's okay. Small means we can against our H0. But if your p-value is large, what does it mean? A large p-value means you would need a very loose significance level to reject. So it's evidence in favor of H0 means we cannot reject H0, right? You see here. Let me give you an example. Suppose we have a p-value equal 0.049 and another one p-value equals 0.001. Basically, both of them can reject at 5%. Right? Both of them. But look at the same under the old approach. But here, 0.001 is much stronger evidence. Okay, this is more strong. It's more strict and stronger, right? So the p-value shows you the difference. A simple reject or don't reject decision hides it. The thing that you need to know from this slide is smaller p-value equals stronger evidence, reject H0, okay? Where does p-value come from? Do you know where does p-value come from? Fisher? The table? Oh, t-score, yeah, exactly. Yeah, yes, exactly. Okay, so there's one point. My professor, when I studied PhD, my professor, actually, he's the top 2% scientists, okay, in the world. He doesn't believe p-value. You need to know that, okay? You can search after the class, what is p-hacking? You may be interested, okay? So for the thing that we learned so far, t-value, t-ratio, p-value, those are frequentist statistic. So you know that in statistic, there are different, how should I say, different opinions, right? So they have different groups of scientists, like in economists, right? We don't have the same. So in statistics, if the one who use p-value, t-ratio, those kind of thing, we call them frequentist. And another one, the opposite one, is Bayesian. Bayesian, have you learned about this one? Yes, you do, with Arthur and Alice. Bayesian statistics, okay? I still show you those t-ratio, p-value because we follow the traditional statistic, which is frequentist, okay? But you have to know, you have to beware of p-hacking. What does it mean, p-hacking? Like in economics, right? When we do our research paper, suppose you got 50 observation and then you run your estimation model. And then you test each variable. It shows insignificant. What does it mean? Your X doesn't affect Y. So what do? Because we want to get the significance, right? We want to reject H0. Otherwise, you cannot go and present. You cannot go and present your work. The committee, they will question you. So what do we do? We go and get more data, right? We go and get more data in order to get the significance one. This is p-hacking, okay? Because we can torture our data. Do you believe that? We can torture our data. Because this is about human manipulate, right? So you need to be critical and questionable every time when you read a paper. Okay, be careful. But at least you should choose some paper that is from a good journal. You need to know how to distinguish a good journal. We have a ranking, the whole thing, okay? If you are interested, you may search p-hacking. Be aware of that, okay? That's why, this is why econometrics is still developing right now, okay? Still keep going right now. Okay, let's continue. How do we actually compute a p-value? Let's see it virtually, okay, from a two-sided test. Suppose our observed t statistic is 1.285, okay? The p-value asks, what's the probability of getting a t-ratio this extreme or more extreme just by chance if h0 were true? This is the logic of p-value, okay? You see? If you ask a Bayesian statistician, they will see this logic is wrong. But I don't want to confuse you now. So here, let's follow this one. Here, we want to know what is the probability that our t-ratio is greater than 1.85, okay? So this is how we calculate probability. And then, why it's 2 times 0 point something? Why? Because here is two-sided, right? Let's find the area of probability, which is greater than 1.85. This is the area beyond 1.85, okay, on the right, plus on the left. And this is the area, which is 0.035, because we have two sides, right? That's why we use this one times 2, which is 0.0718. So our p-value is 0.078, about 7.2%. Now, let's connect this back to what we already know, all right? At a 5% significance level, what is our critical value? Still remember? At 5%, what is our critical value? It's something around 1.96, okay? So let me write it down here. You see here, 1.96 is somewhere here, right? It's greater than 1.85, okay? So basically, if we use our 5% critical value, there's some part that we cannot reject, right? Basically, we are narrowing the rejection region. Okay, if the t statistic is too large, let's see, here is probably 2. So the rejection region becomes smaller and smaller. That's why sometimes if we want to find the p-value, okay, we just lose it to let the rejection region becomes wider and wider. This gives us a clean and general rule, okay, and it's the most important takeaway from this slide, okay? We can reject H0 if and only if the p-value is smaller than the significance level, right? Basically, our p-value 7.2 cannot be rejected at 5%. But it can be rejected at 10%, right? Okay, so you need to remember, since you got p-value, but actually our programming gonna compute for you, okay? They will show you the p-value. So basically, you just compare your p-value with our critical value, 1%, 5%, 10%, okay? Guidelines for discussing economic and statistical significance, okay? Can you read by yourself and then I'm gonna summarize for you? The first one, if it's significant, you also need to check the size of the effect, which I show you here is the magnitude. Okay, so if it's statistically significant, you also need to check the size. All right, not just the fact that it's non-zero. Remember the school size example? Let me go back to the school size. Here, the skipped our variable, this variable is statistically significant, but you see the effect 0.083, which means very tiny. Okay, so next time when you got a statistical significant, you also check the size. This is the first point. Next one, the fact that a coefficient is statistically significant does not necessarily mean it's economically or practically significant. Okay? Statistically significant does not mean economically significant. Keep this separate. And next one, if a variable is statistically and economically important, but has the wrong sign, but significant, that's a red flag, okay? Maybe your model is misspecified. Like in microeconomics, our price effect. Let's see the consumer's expenditure. Okay, consumer's expenditure, Y equal beta 0 plus beta 1 price. According to the law of demand, the beta 1 should be positive or negative, according to the law of demand. Negative, right, that's right. But if your model, if your regression shows a positive, you should be careful, okay? Because the law of demand is the only law that we have, okay? So you need to check your sign as well. Does it follow our economic theory or not? Next one, if a variable is statistically insignificant at the usual level, 10%, 5%, or 1%, one may think of dropping it from the regression. Okay, so when you run your regression and that variable is not your core experimental variable, and if it's not significant, you may consider dropping it. Okay? But remember, we have omitted variable bias and multicollinearity. Those are the trade-offs, okay, of selecting variables in your model. Next one, if your sample size is small, Effects might be imprecisely estimated so that the case for dropping insignificant variable is less strong. Again, okay, small sample caution. Fewer observations means larger standard errors. Okay, so insignificant might just mean imprecise, not truly zero. Don't drop too quickly when n is small. Clear about those guidance? This is very useful and practical when you do your own research. Confidence interval, new topic again. Remember theorem 4.2? Okay, so here, the same theorem, okay, just different way of using it. We take theorem 4.2 and then we rearrange it a bit. And we get beta j hat minus, this is critical value at 5%, right? Times standard error of beta j hat. Basically, this is our lower bound of the confidential interval, right? This is our lower bound. And if we plus our critical value times the standard error, here gonna be our upper bound of the confidential interval. What does it mean here? What is confidential interval? And here is the calculation and also manipulation of a confidence interval. You see, because we use the 5% critical value, and then we're gonna get our confidence interval at 95%, right? So instead of testing one specific value, a confidence interval gives us a whole range of plausible values for beta j. Okay, let me write it down. Confidence intervals gives us and you should be careful with interpretation, okay? This is the tricky part. The bounds, okay, the lower bound and upper bound, they are random. They are random, right? Because it depends on your estimation result. If this one change, your bounds gonna change as well. So the bounds here are random. But beta j is the true only one population. This is fixed, but the bounds are random, okay? This confidence interval gonna moves around from sample to sample. Let me finish this one. What does this mean? This means if we repeated this sampling many times, repeat and repeat, and build an interval this same way each time, 95% of those intervals would contain the true beta j. It's a statement about the procedure, not about this one specific interval. This is the interpretation. In repeated samples, the interval that is constructed in the above way will cover the population regression coefficient in 95% of the case. As I told you before, so suppose we're gonna have one project and each of you guys gonna have different sample size, right? So different sample size means you're gonna get different beta hat and another different beta hat, right? Everyone has a different beta hat. So confidence interval tells you the range of our estimated coefficient, okay? And 95% of those interval would contain the true beta j. Let me write it down. But one point is that as long as your model is correctly specified, and also you don't have a multicollinearity in the generality issue, your guys' estimate beta j hat will be different, but maybe just slightly different, okay? It should be close, not jump a lot. Clear about confidence interval? Again, the confidence interval depends on your estimation, right? So it's random. The upper bound, lower bound, the bounds are random. Next one, confidence interval and testing. Same idea, okay? We have 3 common confidence intervals. 99%, 95%, or 90%, okay? Here we just plug in different critical values, right? This is critical value at 1%. Okay, I showed you here, 5% and 10%. Just like p-value, okay? P-value and also the t-ratio. So right now here we have confidence interval, but basically they follow the same logic, all right? The same logic. Let's see the pattern. If the confidence interval is higher, which means you have a bigger or small critical value. If, okay, you see here from 90% to 99%. So here the confidence interval is higher, right? Same here. If higher confidence interval, which means bigger critical value, right? Bigger critical value. And wider interval. Makes sense. To be more confident of capturing the true beta j, you need a bigger net. Let's see the connection to what we already learned, okay? Confidence interval and hypothesis testing. They are really two sides of the same coin, okay? Two sides of the same coin. Let's see the rule. If AJ falls outside the confidence interval, this is equivalent to rejecting our H0, beta j equal AJ at the corresponding significance level. This is the relationship between confidence interval and hypothesis testing. Okay? Let me repeat. If AJ falls outside the interval, this is equivalent to rejecting H0 and in favor of H1 at the corresponding significance level. Let me finish 3 more slides. Okay, so here I showed you an example. I'll give you some time to understand it by yourself, and then I'm gonna summarize for you. Page 27. Could you please look at this example? And this is about confidence interval, okay? What does it mean? The example is about firms' research and development expenditures, okay? So here's our model. Log RD hat equal beta 0 plus beta 1 log sales plus beta 2 profits as percentage of sales. So here, RD is research and development spending. This is RY, okay? Spending on R&D. Sale is annual sale. And this is the profit as percentage of sale. Be careful about the sample size, which is 32, and R square is 0.918, degree of freedom, 29. And here, we use the critical value at 5%, okay? For log sales, here, how to calculate the confidence interval? You need to look at the formula here, right? Beta j hat minus the critical value times the stand error. Okay, you try. This time we choose the 5%, right? So here, 1.084, this is our estimate results, plus or minus critical value times stand error. You have to know how to calculate this one. This is the confidence interval for log sale, right? And then we got 0.961 to 1.21. Notice fairly narrow interval, right? From 0.9 to 1.21. So this is narrow, quite narrow. So this effect is precisely estimated. Since 0 is not in this interval, so this coefficient is statistically significant, right? So I'll write down 0. How do we use? Okay. 0 falls outside of this interval, okay? Which means I showed you the effect of sales on R&D is relatively precisely estimated as the interval is narrow, right? Moreover, the effect is significant different from 0 because 0 is outside the interval. Next one, how about profits as percentage of sale? Do you know how we calculate it? I hope you do. And here is the confidence interval for profits, right? And this interval is much wider. This interval is much wider, which means imprecisely estimated. And my question is, does 0 belong to this interval? Yes. 0 is inside this interval, right? Which means the profit as percentage of sale is not statistically significant, right? Clear about the confidence interval here, but basically we don't use it much. We use p-value or t-ratio more often, but no confidence interval, okay? But they have the same logic, all right? They have the same logic. Basically, for confidence interval, you should understand the formula, okay? And then compare it. So here, actually, we use our hypothesis is that, okay, for the pink one is beta 1 equals 0, right? That's why I showed you here, 0 is outside the interval, okay? So which means we can reject H1. Sorry, we can reject our null hypothesis, H0. For the blue, our hypothesis is beta 2 equals 0, right? And since 0 is inside this interval, which means we cannot reject H0, okay? Take a look at this slide. What if the hypothesis involves two coefficients together, not just one? Because before I showed you beta 1 equals 0 beta, but it's only one beta. What will happen if two coefficients together, not just one? Okay, so you see the example. Here, actually, we're gonna test hypothesis about a linear combination of the parameters, which is beta 0 and beta 2. Here is the example. Let's see the example. Log wage equal beta 0 plus beta 1, GSC plus beta 2, universe plus beta 3 experience plus mu. So our hypothesis here, we want to test that the null hypothesis H0 means beta 1 minus beta 2 equals 0 against alternative H1, beta 1 minus beta 2 is less than 0. So we want to know the question is a year, you see, beta 2 means years of education at 4-year college, and beta 1 is years of education at 2-year college. So right now we want to test the difference between 2-year college or 4-year college. That's why we take beta 1 and beta 2. We want to see their difference, okay? So here our hypothesis H0 becomes beta 1 minus beta 2 equals 0. If this is true, that means 2 years education equals 4 years education, right? And our hypothesis is beta 1 minus beta 2 less than 0. Okay, so here we have a possible test statistic would be the same logic, right? Estimated divided by the stand error, okay? So here we're gonna use beta 1 hat minus beta 2 hat divided by the stand error of beta 1 hat minus beta 2 hat. The difference between the estimates is normalized by the estimated standard deviation of the difference. About this formula, the null hypothesis would have to be rejected if the statistic is too negative to believe that the true difference between the parameters is equal to 0. But here is the catch, and it's the whole point of this slide. We can't just combine SE beta 1 and SE beta 2 separately. We need the stand error of the difference, which is beta 1 minus beta 2. Because this requires not knowing how beta 1 hat and beta 2 hat covariate, okay? We need to know their covariance, which I'll show you in this slide, but I'm not gonna cover it today. I just want to let you know about this T ratio, how we compute it if we want to know two parameters, okay? If our hypothesis is not only 1 beta, it's 2 beta, how we compute the T statistics. I'll show you detail later, but not for today. I think I'm done for today, okay? I still need one more lecture to finish this chapter. And after I finish this chapter, we're gonna have lab 2. Okay, lab 2, but not on this Wednesday because I haven't finished this chapter. Okay, when I finished my side and okay, finally I saw some of you. So if no question, thanks for coming. See you on Thursday. I will not upload new recording for you, okay? I think it's too much. Just try to catch up and watch the part that you didn't understand, all right? So I'll see you on Thursday, okay? Thursday. ขอบคุณค่ะ